Alright everybody, welcome to a new practice exercise for time complexity. So, as you can see, we have the function print pairs, which has only one argument, right, which is n, and its job is basically to print each and every pair of integers I and j, right, that are part of the range 0 and minus 1, and of course I is less than j. So, let's take an example to really understand what the function does, and then let's jump into analyzing its time complexity, right? So I can take a simple example here. I can say that n equals 3, right? Let's see what happens when n equals 3. Well, I'm entering the first for loop, right? Where I have each value for I, right? Starting from 0 all the way to n minus 1, which in our case, n minus 1 is 2, right? So the first iteration of the first for loop, right, is for I equals 0. Awesome. Now, for this iteration, what I'm going to do is, of course, enter the second for loop. And I need to see here what happens. J will take each and every value between I plus 1 and n minus 1. So, I plus 1 obviously equals 1, and n minus 1 equals 2, right? So, I'm going to basically have J equals 1, J equals 2, and that's it, right? I basically print the pairs 0, 1, right? I equals 0, J equals 1, I equals 0, J equals 2, this is 0, 2, right? So as you can see, when I equals 0, I have printed two pairs. Now, what happens is that now I have finished this for loop, and I return to the main for loop, and of course I'm going to increase the I, right? So the second iteration of the first for loop is of course when I is equal to 1. What happens is that we enter again the nested for loop, right? And j starts from I plus 1, so j equals 2 initially, right? And j goes all the way to n minus 1, which is 2. So j is only equal to 2, right? So we only print the pair 1, 2. And of course, we have in the end the third step of this algorithm, which is actually I becomes equal to 2, right? N minus 1. And then we enter and j will be equal to 3, but j has to be less than or equal to n minus 1, which is 2, right? So this range I plus 1, n minus 1 will actually become 3, 2, which is not a valid range, right? So yeah, nothing's going to happen here. We are not going to print anything. We go again, I becomes equal to 3, right? Because I gets increased in a for loop. And of course, this is not good because the range 0, n minus 1 is the range 0, 2, right? So nothing actually happens here. Cool. So as you can see, we have printed 3 pairs of integers. Now, we really understood what the algorithm does. Let's think about its time complexity, right? What do we have to do when analyzing time complexities? Well, first of all, I want to point out something really important. Lots of you are going to see the algorithm and be like, oh, that's super simple. We have 2 nested for loops, a for here and a for here. So definitely from all the algorithms that I've seen in my life, when I have 2 nested for loops, that's definitely big O of n squared, right? Well, in this case, it is, but that's not always the case, right? We're going to see a lot of problems where, especially when you're going to see the amortized time complexity lesson, where we can have 2 nested for loops, 3 nested for loops, and of course, the time complexity is not necessarily n squared or n cubed, right? So please avoid that mistake and really go deep into the analysis. Don't just look at how many for loops are nested and stuff like that and I come up with the answer, right? So what we are going to do first in this algorithm is see what are our fundamental operations, right? The constant operations. And I have a for loop, and I have this printing, right? So this line prints 2 integers. Printing 1 integer, of course, is constant, right? 1 integer, I don't know how many digits can we have. Let's say we have 4, 5, 6 digits, right? If n is something like 10 million or something like that, right? So yeah, don't worry about printing 7 characters, right? Those 7 digits of the numbers I and j. So this could be with no problem considered to be a constant operation, right? Now, this is the only constant operation of this algorithm. Now we have to ask ourselves for how many times we actually execute this operation, right? Well, this is determined, of course, by our two nested for loops and how they work together, right? Now, there are two ways of doing that. The first way, which is more like for advanced people, is you can already look like only at the algorithm, only of those lines, this code, this pseudocode actually, right, in this example, and start like always with the second nested for loop, right? And think about this. Okay, I have to figure out how many iterations does the second for loop, right? So as you can see, this number of operations is not actually constant, right? Because when I equals 0, j was 1 and 2, right? So I had two iterations here for I equals 0. When I was 1, I had only j equals 2, so I had only one iteration. When I became 2, I don't even have an iteration at all, right? So this number depends on I, definitely on the value of I, right? As I said, one who is more advanced in this would take a look at this range, I plus 1 and minus 1, right? So what we know for sure is that when we enter this for loop, what are the values that j is going to take? Well, j is going to go through the following values. First of all, it's going to be equal to I plus 1. Print this, go back, j gets increased and is going to be equal to I plus 2, right? Print this, get back, j gets increased is going to be equal to I plus 3, print, get back, and so on and so forth until, of course, we hit the last value for j, which will be n minus 1, right? So on each different iteration of this for loop, j takes a different values in this set. How many values are here in total? Well, we start with I plus 1 and end with the value n minus 1, right? So as you can see, of course, these values are consecutive, right? Because this is a range. And yeah, the question is how many distinct numbers are there in a range? Well, yeah, you can mathematically tell that, or you can just take an example. Let's say I'm going to take as an example a range, something random, doesn't matter, 4, 9, right? How many integers are in the range 4, 9? Well, 4, 5, 6, 7, 8, 9, right? So 4, 5, 6, 7, 8, 9. That's 9. That's 6 integers, right? Why is that? Well, it is pretty simple. You can look at it this way. The range 4, 9 is actually the range 1, 9, right? So if I write here the range 1, 9, each and every integer from 1 all the way to 9, you can see that here we have 9 integers, right? But I only need the range 4, 9. So I only need to start here. So from the range 1, 9, right? Let me clear this. So from the range 1, 9, I basically get rid of the first 3 elements. So of the range 1, 3. And this is exactly how I get my range 4, 9. Correct? Cool. So the number of elements that the range 4, 9 has is going to be equal to the number of elements that the range 1, 9 has minus the number of elements the range 1, 3 has. Okay? So the range 1, 9, obviously this is simple. If you take all the numbers from 1 to some specific number, the number of elements is indeed that specific number, right? So from 1 to 9 we have 9 integers. From 1 to 3 we have 3 integers. So 9 minus 3, that means that in the range 4, 9 we have 6 integers, right? So be very careful about this. This is a super nice way of counting, I don't know, the length of some subarray maybe, or how many integers are there in a range. We are going to use that a lot, right? So this is how you should think about it. Now, let's get back to our range. What is our range? Our range is the range I plus 1 and minus 1, right? Now, of course, I don't know the exact values. It's not 3, 9 always. It's not 4, 12 always, right? They differ. But I'm going to write it like this. I have the range I plus 1 and minus 1, right? In order to see how many elements are in this range, I'm going to do what I did at the previous step. I'm gonna write this as the bigger range, which starts always from 1. So the range 1 n minus 1, from all the numbers from 1 to n minus 1, if I remove all the numbers from 1 to where? The first one here is I plus 1, right? So I have to remove all the numbers less than I plus 1. So from 1 to I will get this range, right? So how many elements do I have in this range? From 1 to n minus 1, n minus 1. Cool. How many elements I have in this range? From 1 to I elements. Awesome. So in this range, I'm going to have a total of n minus 1 minus I elements, right? So n minus 1 minus I elements, right? Awesome. This is how we always count how many elements are there in a range, right? So as you can see, in a range x, y, if we call this x, y, the number of elements is y minus x, it's y minus x plus 1 actually, right? So yeah, but this is how you prove it. You can always do this on paper until you really like understand it and you remember the formula eventually, right? So my point was that now that we know this demonstration, right, one advanced people who already, solve a couple of problems like this is gonna tell, oh, okay, this nested for loop does a number of operations that definitely depends on the value of I, right? So I take it first into consideration, and the number of the operations is n minus 1 minus I. Awesome. So for each different value of I make this number of operations. Let's just, for example, check it out here to see if we are correct. For n equals 3 and I equals 0, how many operations should I make, right? When I equals 0 and I enter this for loop. Well, 3 minus 1 minus 0, that's 2 operations. And indeed, I have 2 operations, 2 values for j. But when I equals 1, well, when I equals 1 and I enter this nested for loop, I'll have 3 minus 1 minus 1, which is 1. Awesome. When I equals 2, 3 minus 1 minus 2, which is 0. Exactly it, right? So we started from this second loop. And now think about this. For each and every value of I, you actually make this many operations. So what I have to do here is take each value of I from 0 to n minus 1, and for each value of I, add to the total number of operations this number, right? So again, let's say we take I equals 0, right? When I equals 0, the number of operations that I do is n minus 1 minus I, right? So I make a total of n minus 1 iterations in this second for loop, right? Those n minus 1 iterations are, of course, for each and every pair, like 0, 1, 0, 2, and so on and so forth until we hit, of course, 0, n minus 1, right? Makes sense? So this is where we get these n minus 1 operations, right? Now, for I equals 1, right? Because after this n minus 1 operations, I finish the for loop and I go back in the first one. I got increased, so now I equals 1. I have to see, for this I equals 1, how many operations do I do here, right? So, if I equals 1, well, n minus 1 minus 1, right? So I have n minus 2 iterations, right? And again, those are for the pairs 1, 2, 1, 3, 1, 4, dot, 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 1, n minus 1, right? Now, after I finish this, I becomes 2. The number of iterations, n minus 1 minus 2. So it's going to be n minus 3, right? And so on and so forth until eventually I takes its last value, right? Which is n minus 1. So I is going to be equal to n minus 1. And the number of operations is n minus 1 minus n minus 1, right? So it's 0. So think about this. For I equals 0, this many operations. Then for I equals 1, this many operations. I equals 2, this many operations, right? So in total, because we try out each and every value of I, we are going to add all these numbers of operations together, and that's the total number of operations that we get, right? So the number is, let's count it in reverse order. I start with 0, then of course the next one is 1, the next one is 2, and so on and so forth, until of course I hit the last value, which is n minus 1, right? Now, of course, we don't care about the 0, don't worry about it, and we have basically this sum. Now, this sum, you might know from math, right, that it is called the Gauss sum. If you don't know, don't worry about it, just Google Gauss sum, the Gauss sum, right? And the formula for this, which is actually pretty simple to prove, we're gonna do that probably in another video. It is like the last number, which is n minus 1, crossed, we add 1 to the last number, so n minus 1 crossed n, right? Everything divided by 2, right? So take the last number, multiply it with the next one, right? And all divided by 2. Awesome. So we have finally found out the total number of operations our algorithm does. It is n crossed n minus 1 divided by 2. And what we do, of course, when we analyze time complexities, we don't care about constants. So from the total number of operations, we can like forget about the 2, don't take it into account, and with this n minus 1, forget about the minus 1, right? So we are going to have an n crossed n, right? Which is an n squared. Like this is the upper bound, and this is the number that we care about for the time complexity. So indeed, the time complexity of this algorithm is big O of n squared. But the real proof of this is not that 2 nested for loops and that's it, big O of n squared, right? So again, take a small example like we did here. If you are more experienced, you can skip this step and you're gonna find out that, yeah, this number of iterations depends on I. Let's see what's the formula for this, and let's take each value of I and add them together. But if you are not that experienced, that's definitely fine. Take small examples like I did here, n equals 3. And I just said, I equals 0, j equals 1 and 2, 2 operations. I equals 1, j equals 2, 1 operations, right? So here, 2 operations, here, 1 operation, here, 0 operation. Oh, I see a pattern here, right? They are decrementing for each value of I. Why is that? And then you can go in depth into the analysis, right? Now, this is one way of computing the time complexity of this algorithm, which I really like because, you know, I'm the technical type of guy. I really like to prove things and stuff like that. But we can also do it in another way, which is prettier. And yeah, you might find it a little bit easier, and I don't condemn you for that. But unfortunately, the technique that I'm going to show you right now is not like, couldn't be applied to each and every algorithm that you see in your life. But it is pretty cool. So you can think about it like this. What I do basically here is that I take a value for I and I take a value for j. And for each of these pairs I, j, I just print the pair, right? So I can think about what are the values that I and j in this pair I, j take. So as I see, I starts from 0 and goes to n minus 1. So if let's say I make a table, let's call it a table, I don't know, right? And in this table, I basically have here the values that I can take on the rows, right? So I can be 0, I can be 1, I can be 2, until, let's actually take an example. Let's take a small example because this is better to show. Let's say n is 5, right? So 0, 1, 2, of course, I can be 3 and I can be 4. Now, j. J, of course, can be anything from I plus 1 to n minus 1. Yeah, depends on the value of I. So what I'm going to do is not complicate myself. Also, let's have all the values from 0 to n minus 1 here for the columns, right? So I have basically this grid, right? You can imagine this grid with 5 rows and 5 columns, right? Let me clear this to make it pretty. And as you can see, and as I said, the rows are the values for I, and the columns are the values for j. Now we have to look at our algorithm and see which of these cells, because in this grid, if the row is a value for I and the column is a value for j, this means that one cell of this grid is actually going to be one pair that we are going to print, right? So we need to see what cells we actually print, right? We actually cover with this algorithm. So I first equals 0. J will start from 1 and go to n minus 1. So I equals 0 means this row number 0, j equals 1 all the way to n minus 1, which is 4. So I basically take into account these cells. I print these pairs, 0, 1, 0, 2, 0, 3, 0, 4, right? Now, what I'm going to do is increase I. I becomes 1. So now I am on row number 1. J starts from 2 and goes all the way to n minus 1, which is 4, right? So I'm going to take into account these cells. Now, I becomes 2, row number 2. J starts from 3. So what I do is this. And then I becomes 3. J starts with 4 and ends, of course, with 4. And then I becomes 4 and I don't do anything, right? So, as you can see, the number of pairs we have printed and also the number of iterations or operations our algorithm does is the number of cells that we have marked in this grid. And what's the beautiful thing about this? As you can see, you can notice the pattern that the cells that we have just marked, right, are almost 1/2 of the whole grid, right? So if I also had these cells, right, on this diagonal, actually I would have had like almost 1/2 of the grid, right? So how many cells does this grid have? Well, it has like n values, right, from 0 to n minus 1, and n rows, sorry, and n columns from 0 to n minus 1 also, right? So this grid has a total of n squared cells. And as you can see in the pattern, this was an example like for n equals 5. It was a small one, right? But no matter the value of n, as you can see in this pattern, we only take less than half of all the cells in this grid, right? So the number of operations will actually be less than n squared divided by 2, right? But we don't care about the 2, and we can say that this is our time complexity. This is a more visual way of coming up with complexities, but as I said, it's not going to be applicable or very useful to all the problems that we are going to encounter. All right, everybody. I hope you really understood the lesson. I hope it was really clear. And yeah, see you in the next one where we are going to analyze an algorithm which is a little bit harder. So, see you there. Bye.